So today I will talk about the Poisson distribution. More specifically, I will talk about how to derive the moment generating function, and then after having done that, how to derive the moments of a Poisson distribution. Only the first two for a matter of simplicity. First of all, I have to define what the probability mass function of a Poisson random variable. In this case, we deal with a PMF because the Poisson it is a discrete random variable and not a continuous random variable. Therefore, let's denote k tilde as Poisson distributed with parameter lambda, with lambda strict to positive. Then the probability that k tilde is equal to k it is equal to this formula that is the common one with the constraint with the requirement that k goes from 0 to plus infinity and it is an integer. So at this point we are able to get the moment generating function, which is the expected value of the exponential of the product between t, which is an integer and it is positive, strictly positive, and then the random variable of interest. Therefore, we get this summation. A smart thing to do is to take out the what does not depend on the index h. We take it out from the summation, and inside the summation we have the series expression for for an exponential function. More specifically, the Taylor series of an exponential function, which is this result. Therefore, the final result, which is that the moment generating function of Poisson is the exponential power lambda multiplied by exponential power t minus 1. At this point, we are able to get the moments of the random variable by taking the derivative with respect to t and then placing t equal to 0. The first derivative with respect to t of the moment generating function, it is this product, because we have to recall what is the chain rule for deriving product of function, because in this case we deal with a function which is a function of t. So we have that our f, it is exponential of lambda power multiplied by exponential power t minus 1. And then our g of t in this case, it is lambda multiplied by exponential power t minus 1. Therefore, as it is written in orange, the first step is to derive the derivative of f of g of x with respect to g of x, and therefore it is exponential power lambda multiplied by exponential power t minus 1. Then we have to multiply it by the derivative of the function g with respect to the variable of interest. And in this case, it is lambda multiplied by exponential power t. Then we put t equal to 0. We get lambda, which is the mean of the Poisson random variable, which is therefore equal to the parameter which describes the distribution. Then the second step is to find the variance. We recall out there in the grid box the first derivative with respect to t, and at this stage we have to take the second derivative with respect to t. And in this case we we have this result because we have a product of function of t. The first bit it is lambda, the first function it is lambda power exponential power t, and then the second function of t it is exponential power lambda multiplied by exponential power t minus 1. The first bit it is therefore the first derivative, the function of the first derivative multiplied by the second function, while the second bit of this summation it is the first function multiplied by the first derivative of the second function. And then by putting t equal to 0 we get this result before we have the second moments. And then by applying the we know that the variance of a given random variable k, it can be derived by taking the difference between the second moment of the random variable of interest less the first moment power 2, and therefore we get that the variance it is equal to the mean. But this applies only in theory. In fact, in practice it is very difficult that it happens. Normally the variance is a little bit higher than the mean, and in fact for empirical purposes we statisticians use models called over dispersed Poisson model in order to take account for the difference between the mean and the variance of a Poisson random variable. And I say thank to all of people who will see this video, and goodbye.